Hi, I'm Dr. Jeff Groh, and this is Linear Algebra. Linear algebra starts with just an investigation, a deep dive into systems of linear equations. The topic may seem boring or irrelevant to begin with, but you would be surprised. I would like to give you some sense of the importance of linear algebra. In general relativity, the space-time metric is a symmetric 4x4 matrix. A symmetric matrix is one where you can have different diagonal elements, and if you have elements off of the diagonal, they can be anything, but you reflect those numbers through the diagonal. So these numbers will match. The numbers on the diagonal can be anything. You can see with a 4x4 symmetric matrix, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 independent entries. In Einstein's theory of gravity, the spacetime metric is a 4x4 matrix with 10 independent potential functions in each of these 10 spots. In Einstein's unified field theory, he allows for the 4x4 unified field to have independent entries in all 16 locations. In Einstein's unified field theory, he was trying to unify gravity, which has 10 gravitational potentials, and electromagnetism. In electromagnetism, you have the electric field and the magnetic field. These are vector fields, and as you can see, they have 6 entries, not all of which are independent, but there's more than enough room in a 4x4 matrix that is not symmetric to accommodate 16 independent potentials that will cover all of the potentials of gravity plus the 6. You don't really need all 6, but at least you'll have enough room to accommodate electromagnetism as well. Now, it will take a while before you're ready for understanding either Einstein's general theory of relativity or his unified field theory, which is even more difficult. But you cannot truly understand either special relativity or general relativity or unified field theory without an understanding of linear algebra. We are going to spend some time this semester solving linear systems of equations, and all of those linear systems can be expressed as a matrix equation AX equals B, and these will have solutions provided A is invertible of the form X equals A inverse times B. Now, I had a student when I was at the University of California at Davis working on my postdoctoral studies. While I was there, I was teaching the graduate level real analysis course, which is perhaps one of the first courses taken by those newbie PhD students. Now, I was a little bit confused because one of my students was not a PhD student in mathematics. His name was Dmitry Medvedev, a Russian national, and he was taking real analysis despite the fact that he was in the PhD program in chemistry. His father told him that he needed to study some mathematics, so he took my course. Dmitry told me that almost all of his quantum chemistry problems reduced to solving AX equals B. Yep, not only will you use linear algebra in studying special relativity and general relativity and even unified field theory, but quantum theory as well. This is the foundation for quantum theory because, after all, Matrices have an interesting property that matrix multiplication is not commutative. And it is exactly this property that allows for the non-commutativity of observables in quantum theory. In the 1920s, there were two competing theories for describing quantum phenomena. One was the matrix method, and the other one involved solutions of partial differential equations like the Schrödinger equation. It's been shown that these two methods, which seem so different, give you exactly the same results. We are going to make a special study of linear transformations in this course that map one vector space into another vector space. Now, linear transformations always satisfy two properties. When you take the linear transformation of the sum of two vectors, you can apply that linear transformation to each of the entries separately in that sum. Also, constant factors can be factored out of linear transformations. So these two properties will characterize all linear transformations. In this course, we will show you how to represent linear transformations by matrix multiplication. But you ought to be aware that operations like the derivative is a linear transformation. I'll even show you how, in some special cases, to represent the derivative by matrix multiplication. In addition, what about the integral? Even the integral can be represented by a matrix. We will learn about dimensions of vector spaces and bases and diagonalization of matrices that are diagonalizable, and those that are not diagonalizable, we might have some other ways of dealing with those. You can't even imagine the things that you're going to do in this course yet. Yet, you must be willing to go through a large number of mind-numbingly boring arithmetic computations as well. So there are certain characteristics of this subject that you're going to learn to love or hate. And one of those is all the mind-numbingly boring arithmetical computations. It's good for you. Just stick your horns down and bull forward. Also, you're going to have to get used to proof, mathematical proof. We are going to train you to construct simple mathematical proofs based on definitions typically and basic theorems. You may be surprised at how much the rest of your training is affected by this one topic. Linear algebra is sometimes thought of by mathematicians as the first real mathematics course that students take. Why do we think this? We think this because this is the first course where we systematically train you to construct short proofs. Now, proof is the coin of the realm in mathematics. When you work on a PhD in mathematics, you are required to prove new theorems, develop a new theory, extend the boundaries of mathematics, and if you don't have a proof, then you got nothing. Truth is the core value of the mathematician. So, we'll start off with solving linear systems of equations. I guarantee you that this will involve mind-bogglingly boring arithmetical computations, and a lot of them. Even so, the theory underlying all of this that we are developing will help train you to think rationally and to construct proofs. There is one very important element of your training that you will have to be careful about, and that is you need to understand what the words that we introduce mean. Definitional meaning as well as procedural and functional meaning. And there is a difference. One of the chief difficulties that students have from an early age in mathematics is dependent upon a good understanding of the meanings of the words involved. And if you don't understand the meanings of the words in mathematics, you're apt to make errors of false generalization and all kinds of foolish mistakes just because you don't understand the meanings of the words. In almost every other area of human inquiry, that formal meaning is of less importance. In fact, most people prefer just an intuitive understanding. They like to pick up meaning by osmosis, if you will. Let me give you an example. What is an item of furniture called a table? What is it? Can you tell me? Think about that. What is an item of furniture called a table? A lot of people will think, well, looking at a table, it's a flat level surface with legs of some kind. Not necessarily so. It could be hanging from the ceiling by chains, I suppose, but how flat is flat? How level is level? Could the surface of the table be made with pebbles and be rough? I think you can see the definition that may be given in Merriam-Webster might not even be a very good definition. Table is a form of tool. It is used for a purpose or purposes. I say that a table is a freestanding item of furniture besides which one may sit, and upon which one may place items for ease of manipulation or for display. Now, that tells you functionally what that tool does. If the table has legs that are so large that the surface is flush with the ceiling, it cannot serve the function of a table, and hence in my definition would not be a table. You know a table when you see one. You know how to use a table when you're near one. However, if you have to stand next to a table, it's no longer a table, it's a counter. A table could be shaped like a cube, or kind of like a sphere with a flattened top, perhaps. There are any number of different forms that a table can make. It doesn't have to have legs. It could have 1 leg, 2 legs, 3 legs, any number of legs, no legs. But as long as it functions like a table, in my definition, it is a table. Now, the precise meanings of the terms that we use in linear algebra will be important in whether or not you are able to construct short proofs. When you first read a problem where you are asked to prove something, and there will be many such instances in this course, the first thing you should do is think about the precise definitions of the words used. Those will be your guide on what to do. We'll start off with linear systems of equations. Suppose I have the equation 3x plus 2y equals 5, 5x minus 3y equals 7. This is a system, a linear system in two equations in two unknowns. A nonlinear system might have other functions like x squared or x times y. Those are not permitted in linear systems. In linear systems, the variables can appear once in the numerator in separate terms. You can have a constant term, but x, if it appears, will appear once in the numerator of a term, and y will not appear in the same term. Y will appear in a separate term. A linear system like this you've been solving since Algebra 1. Each of these equations represents a straight line. When you solve the system of equations, you look for the point of intersection of those two lines, because that's the point that, when substituted into both of these equations, yields a true statement. Another point on one of the lines will make one of the equations true, but not the other. As you can see, if the lines are parallel, there may be no solutions, no points common to both of the lines. It is also conceivable that the lines could be different representations of the same line, in which case every point on that common line will be a solution. As you can see, there are three cases: one solution, no solutions, and infinitely many solutions to these linear systems. This will be true in general. A system of linear equations is a collection of equations of the following form. Let's suppose that our variables are x1, x2 through xn, and constants, coefficients, are a11, a12, x2. So we have constant times variable plus constant times variable. We're going to keep going until we get to a1n, xn equals b1. These coefficients are the coefficients of the first equation. The coefficients of the second equation will begin with a 2. So a21 x1 plus a22 x2 through a2n xn equals b2. How many equations can we have? In this course, we will assume that the number of equations is finite. So we'll go to some number m, am1 x1 plus am2 x2 plus amn xn equals bm. So we'll have perhaps m equations in n unknowns. We call this an m by n system. This is called the order. As an example, suppose we have 4x plus 3y minus 2z equals 1, 5x plus 8y minus z equals 7. This would be a 2 by 3 system. That will be its order. It has two equations in three unknowns. What is a solution to a linear system? It's a point that, when substituted into each of the equations, yields a true statement. Let me ask you, is minus b plus or minus square root b squared minus 4ac all over 2a an equation? The answer is no. There's no equal sign. Where's the equal sign? An equation is two expressions separated by an equal sign. In this sense, every equation is an assertion of truth. This is that. Now, there are three kinds of equations. First of all, if I have x plus x equals 2x, for what values of x is this equation true? The answer is, for all substitutions of the variable, this is true. That's why this is called an identity. It is identically true, and sometimes we may even write x plus x is identically equal to 2x. The triple equals means true for all substitutions of the variable. It's identically equal to. That's different from 2x plus 3 equals 0. For what values of x is this equation true? This is true for x equals negative 3/2, but it's not true for any other replacement of the variable. This is called a conditional equation. It is true sometimes, but not at other times. You solve conditional equations. You prove identities. There is yet a third kind of equation. For what values of x is the equation x plus 2 equals x plus 3 true? The answer is, this equation is not true for any replacement of the variable. That's why this is called a contradiction. Now, I ask you, is 2 equals 3 an equation? The answer is yes. It's two expressions separated by an equal sign. It's just false. Not every assertion of truth is true. So this is false, but it is an equation. The solution set of a system of equations is the set of all solutions. All solutions. A system of equations, as we've seen, may have infinitely many solutions. The solution set will include all of them. This is also sometimes referred to as the general solution. If a linear system has one or more solutions, then it is called consistent. If it has no solutions, the only other possibility, it is said to be inconsistent. So an example of an inconsistent system might be parallel lines, or if you have three lines, lines that do not have one common point of intersection. A system is in upper triangular form if the coefficients below A11, A22, A33, those are called elements of the main diagonal. If those elements below the main diagonal all have coefficients equal to 0. For all, we're assuming that the coefficients are 0 whenever the row number is bigger than the column number. So for example, if I have A11x1 plus A12x2 and then A21x1 plus A22x2 and A31x1 plus A32x2 and so on, this would have to be 0 and these would have to be 0. Everything below the main diagonal will be 0. We'll just put a big fat 0 under the main diagonal. Just thinking vaguely in terms of the form of the system of equations. The system of equations will have stuff in the upper triangle, but zeros everywhere else. It is lower triangular if aij is 0 for all I less than j. So lower triangular matrices or systems will have non-zero stuff below the main diagonal and including the main diagonal, but zeros above. I want to give you an example of two different systems of equations. First of all, let's look at 2x plus y equals 3, and how about 3x minus y equals 2. Then consider 2x plus y equals 3 together with x equals 1. Now, it's pretty easy to figure out the solution set to the second equation. A solution set, by the way, is a set. It's a set of points that solve both of the equations involved in the system. To be a solution to the second system, you must have x equals 1. If x is equal to 1, then y must be equal to 1 for the first equation to be true in the second system. 1, 1 also solves the first equation in the first system, and 1, 1 solves the second equation as well. So the set that contains 1, 1 is the solution set to both systems. When two different systems have exactly the same solution set, we say that those systems are equivalent. Two linear systems are equivalent if they have exactly the same solution set. The system is called underdetermined if it has more variables than equations. Let me give you an example. 3x plus 2y plus 4z equals 1. 7x plus 5y plus 8z equals 9. This system, each equation represents a plane in space. If these planes are not parallel, and these particular planes are not, then you should get a line of intersection. We're expecting there to be infinitely many solutions. So in underdetermined systems, you either expect to get no solutions if the planes, for instance, are parallel, or infinitely many solutions, but you do not expect to get exactly one solution for these underdetermined systems. If you have only two variables, an underdetermined system is just a single equation, like this. And if you have only one equation of a line, then the set of solutions will be every point on that line. It will be infinite. Note that for a system of one equation in two unknowns, this underdetermined system, the equation itself constrains the points in the plane. You have one free choice. You may either freely choose x or you may freely choose y. But once you have chosen one of the two variables, the value of the other variable will be determined by the equation. We say that we have one free variable in this case. And if we have two equations and three unknowns, we should still be able to choose one variable freely. The two equations will constrain the other two variables. So we should still have one free variable and two variables that are not free. A linear system is overdetermined if it has more equations than unknowns. So for example, if I have 2x plus 3y equals 5, 7x minus 8y equals 10, and 3x plus 9y equals 17. Here I have equations for 3 lines. This increases the probability that there are no solutions. However, it is still possible that 3 lines could intersect with a common point. We would have to try to solve the system to determine which case we have. Nonetheless, if you have more equations than you have unknowns, the system is overdetermined. Now we're going to review a method for solving linear systems of equations that you've already studied. You know this. But we are going to understand this at a deeper level than you've understood this method before. It's called Gaussian Elimination. Now, you know about Carl Friedrich Gauss, who, as a young boy, 9 years old, was given a problem to solve by his teacher, and I think it was add the numbers from 1 to 100, 1 plus 2 plus 3. The teacher expected the students to be working with their slates for a long period of time. He was purposefully giving them busy work because he had other things to do. So Gauss, as soon as he heard the statement of the problem at 9 years old, wrote the answer down on his slate and turned it down on his desk. Well, in his class it turned out he was the only student who had found the correct answer. And the way he did it was he added 1 plus 100 and got 101. 2 plus 99 gave 101. 3 plus 98, 101. There are 50 such pairs in the first 100 numbers that add up to 101. So the answer should be 101 times 50, or 5050, which he instantly wrote down on his slate and was the only one in his class to get the right answer. Gauss was famous for a number of things. His doctoral dissertation proved the fundamental theorem of algebra. Every polynomial equation of degree n has exactly n solutions, counting multiplicities, and complex solutions. Gauss also invented the differential geometry of surfaces while serving as a surveyor for the Kingdom of Hanover. He noticed that when walking around some mound, you can describe the curvature of that surface by the changing direction of a pole stuck at a 90-degree angle to the surface, normal to the surface. The motion of that normal vector gives you a sense of the curvature of the surface. But there could be principal curvatures in different directions. You can have more curvature in one direction than in another. There will be invariably one direction that has the greater amount of curvature and another direction which has the least. If you take the product of those two curvatures, those principal curvatures, you end up with a measure called the Gaussian curvature. Gauss defined this Gaussian curvature from something poking out of the surface itself. Anything that pokes out of the surface is called extrinsic. Gauss was able to prove that the Gaussian curvature can be calculated by intrinsic means as well, from means only related to tangent vectors to the surface. We think of tangent vectors to a surface as being like velocity vectors for objects that are moving within the surface. So while he defined his Gaussian curvature through extrinsic means, he discovered that it could be found by intrinsic means. He called this the Theorem of Algebra. Or the surprising theorem. He was surprised that this is true. Gauss is sometimes referred to as the prince of mathematicians. He's perhaps one of the best mathematicians since Newton. And before Newton, perhaps Newton was the best mathematician since, say, Archimedes. Gauss is also known, of course, for his method of solving systems of linear equations called Gaussian Elimination. Before moving on and discussing this method, I would like to talk about Gaussian Elimination Day, which is February 23rd. It's a day of high glee for math students everywhere. Gaussian Elimination Day celebrates not only Gaussian elimination, but it's the day to celebrate the ultimate Gaussian elimination. This is the day of Carl Friedrich Gauss's death. When I was earning my master's degree at Idaho State University, Gaussian Elimination Day was a tradition in the department. It was a day where students could be gleeful and happy and perhaps have black cupcakes and black balloons. So that we can talk about Gaussian elimination, we need to talk about elementary row operations. Of which there are three. First, you may interchange any two rows in a linear system. any two equations, that should not change the solution set. If all you're doing is changing the order in which you're listing the equations, the solution set remains unchanged. 2. You may multiply any equation or row by a non-zero number. Of course, if you multiply all of the equations by 0, the entire problem goes away, and you will certainly affect the solution set. However, if you multiply any equation by a non-zero number, that number can be canceled off, and you will not change the solution set at all. Multiplying any, suppose I have the equation x minus y equals 0. This represents the equation y equals x. If I multiply by 2, I get the same line. It doesn't change the points that solve the line at all by multiplying by a non-zero constant. There is one more elementary row operation. The third elementary row operation is you may add a multiple of one equation or row to another. Any multiple. Of course, if you add 0 times one equation to another equation, that doesn't change the system at all. But we're allowing you to add any multiple of one equation to another equation. It might be less clear that this elementary row operation does not change the solution set. We'll have to prove that. Performing an elementary row operation produces an equivalent system. Remember what equivalent systems are. Those are systems that have exactly the same solution set. It should be clear that just interchanging rows does not change the solution set. And number 2 is also pretty obvious. If you have, let's say, x1 hat, x2 hat through xn hat, let this be a solution to a linear system so that AI1 x1 hat plus AI2 x2 hat plus AIN xn hat equals b sub I, where I goes from 1 to n, then if this is a true statement, then so is C AI1 x1 hat plus C AI2 x2 hat plus C AIN xn hat equals C times b sub I. So just multiplying through by a constant doesn't change the truth of the equation. Duh. Now, where we really need the proof is on the third part. We're going to let x1 hat through xn hat solve the system AI1 x1 hat through AIN xn hat equals b sub I, I goes from 1 to m. So this point solves all m of these equations in the system. We want to consider what happens when you take one row, multiply it by a constant, and add it to a different row. Then we'll have c times ai1x1 hat plus ainxn hat plus the other equation aj1x1 hat plus ajnxn hat. If you multiply through by a constant on one equation and add to a different equation, you should get c bi plus bj. C times the right-hand side of the first equation, which was b sub I, plus the right-hand side of the second equation, which is b sub j. So if the point x hat solves the system, it will certainly solve the equation obtained by multiplying one row by a constant and adding to a different row. And does the process go the other way? If you have a solution to this equation, does it necessarily solve the original system? And the answer is, all you have to do is take this new equation, this new jth equation, multiply the ith equation by negative c and add to this, and you'll recover the original system. So it goes both ways. If you have a solution to the original system, it will solve the system where you've multiplied one row by a constant and added to a different row, obtaining a new jth row. That together with the original system. If you have the original system except for the jth row, and that's been altered by one elementary row operation of the third type, you can obtain the original system by multiplying the ith row by negative c and adding to the new jth row. That will eliminate this part. And so we do in fact get equivalent systems because they both have the same solutions. Let's suppose I have x plus 2y equals 3, and then let's say 2x minus y equals 6. Here I have a nice little system. How do I solve this? One idea for solving a system such as this is to perform elementary row operations to try to eliminate variables. Suppose we do the following operation. Negative 2 times row 1 plus row 2 yields a new row 2. That leaves the first equation alone. We're not doing anything to the first equation. What we're doing is taking negative 2 times the first equation and adding it to the second equation. By the last theorem, we know that that process will not change the solution set. So negative 2 times x plus 2x is 0x. Negative 2 times 2y is negative 4y, plus negative y is negative 5y. Negative 2 times 3 is negative 6, plus 6 is 0. You can see that if we multiply the second equation by negative 1/5, negative 1/5 times row 2 yields a new row 2, we have the equivalent system x plus 2y equals 3, and then y equals 0. We are now in something called Row-Echelon form. In Row-Echelon form, we have these little echelons, these little tiers, these little steps. And each step has the first non-zero coefficient equal to 1. Those entries below a leading 1 have coefficients of 0. If you perform a sequence of elementary row operations until it is in Row-Echelon form, it becomes particularly easy to solve the system. In this case, we can see that the last variable, y, must in fact equal 0. We can back substitute into the previous equations to obtain values for the other variables. So in this case, it's pretty easy to see that the solution to the original system is the point 3, 0. There are three principles describing what it means for a system to be in row-echelon form. First, each row must have the first non-zero coefficient equal to 1. It is possible for a row to consist entirely of zeros. That's okay. But if it has a non-zero entry, the first one on the left must be a 1. 2. The coefficients directly below a leading one must be 0. This means that if you have a coefficient underneath but in the same, lastly, the leading ones must trail to the right. So if you have a leading one in one row and a leading one in a succeeding row, the leading one in the row later on must be to the right of the leading one in the first row. So if, for instance, you have an entry aij which is 1, has a leading 1, and you have a leading 1 in a big I, big J, where I is less than J, so this first leading one is higher up in the system of equations, then in fact you must have the big jth column be bigger than the little jth column. We have now defined row-echelon form. There is also something called reduced row-echelon form. The only difference between row-echelon form and reduced row-echelon form is that in row-echelon form we require that below leading ones all entries must be 0. We don't say anything about what happens above the leading ones. In reduced row-echelon form, not only do you have zeros below the leading ones, you must also have zeros above the leading ones. The system is in reduced row-echelon form if it is in row-echelon form and the coefficients above leading ones are 0. have x plus y equals 3 and 2x minus y equals 3. Let's perform elementary row operations to put this into reduced row echelon form. Clearly, if we take -2 times row 1 and add it to row 2, we can yield a new row 2. The first row stays the same. -2 times x plus 2x gives you 0x. -2 times y plus -y gives you -3y. -2 times 3 is -6, plus 3 is -3. We'll then take -1/3 times row 2 to yield a new row 2. We'll have x plus y equals 3, and then y equals 1. This gives us row echelon form. We need one more operation to produce the reduced row echelon form. In particular, we can take negative row 2 plus row 1 to yield a new row 1. That'll give us the second row will stay the same as before. On the first row, we'll have -y plus y cancels out, and -1 plus 3 equals 2. We're now in reduced row echelon form, and we are clearly trailing off with leading ones to the right, zeros below leading ones and zeros above leading ones. You might remember synthetic division way back in pre-calculus. What you did was you eliminated all reference to the variables and just wrote coefficients. We're going to do something similar for systems of equations. We're going to write down the augmented matrix. Associated with a linear system. So if I have, for instance, A11x1 plus A12x2 equals B1, and A21x1 plus A22x2 equals B2, as a linear system of equations, the associated augmented matrix will be A11, A12, we'll put a vertical bar or a dotted slash, B1. This is the augmentation that we're making to the matrix. A21, A22, B2. And I give you the augmented matrix associated with a linear system of equations. All you do is don't write the variables. Instead of the equal signs, you put a vertical slash. We can perform the same elementary row operations on the augmented matrix. You can interchange any two rows of the matrix. That's the same as interchanging any of the two equations in the system. You can multiply any row by a non-zero constant, the same as multiplying an equation by a non-zero constant. You can multiply a row by something and add it to a different row. That's the same as multiplying an equation by something and adding it to one of the other equations. Those operations do not change the solution set to the linear system, and hence we can then solve these systems synthetically by performing the operations on the augmented matrix until we get to either row echelon form or reduced row echelon form. If you're in row echelon form, you use backward substitution to arrive at the solution. If you're in reduced row echelon form, you can just read the solution right off. I've written down a system that I would like to try to solve. Now, we'll write down the augmented array associated with this system to begin with. Note that we first need a leading 1 in the upper left-hand corner of our augmented matrix. I can get that by multiplying the second row by -1 and adding it to the first row. Negative row 2 plus row 1 yields a new row 1. That gives us 1. Negative 1 times this plus this. Negative 1 times this plus this gives me 0. I'll have 4. Negative 1 times this plus this. This gives me 13. And everything else stays the same. From here, we'll get zeros underneath the leading ones by taking negative 4 times row 1 plus row 2 yields a new row 2, and negative 2 times row 1 plus row 3 yields a new row 3. That leaves the first row alone. Negative 4 times this plus this. Negative 4 times this plus this. Negative 4 times 4 is negative 16 plus 1 is negative 15. Negative 4 times 13 is negative 52 plus 7 is negative 45. I know, it's a lot of mind-numbingly boring arithmetic, but in the age of calculators, you folks need this practice. So I'm going to run you through this. Negative 2 times this plus this. Negative 2 times this plus this. Negative 2 times 4 is negative 8 plus 7. Negative 7 is negative 15. Negative 26 and negative 19 is negative 45. You can see then we can get a row of zeros by taking negative row 2 and adding to row 3, yielding a new row 3. We'll have 0, 0, 0, 0. To place this into reduced row echelon form, we need merely multiply the second row by negative 1/2. So we'll take negative 1/2 times row 2 yields a new row 2. We'll have 15 halves and 45 halves, a bunch of zeros. There you have it. This is equivalent to the equation x plus 4z equals 13. The second equation is y plus 15 halves z equals 45 halves. You can see x plus 4z equals 13, y plus 15 halves z equals 45 halves. X will be determined by z, y will be determined by z. Z is the free variable, whereas x and y will be determined and not free. If we allow z to be some arbitrary parameter, how does that affect the solution? You can see then that x will be 13 minus 4 times t. Y will be 45 halves minus 15 halves t, and of course z is t. Our solution set will consist of points 13 minus 4t, 45 halves minus 15t, and t, where t is an element of the set of real numbers. We get an infinite number of solutions. In fact, you might recognize this as the parametric form of a line in space. We started out with a system of 3 equations and 3 unknowns. Each of those equations represented a plane. It appears that these 3 planes intersect in a common line. They have a common line of intersection. These are all the points on that common line. These points solve the system of equation. Let's consider these two planes, x minus 3y minus 4z equals 6 and 3x minus 9y minus 12z equals 24. We'll place them in an augmented array. 1, negative 3, negative 4, vertical slash where the equal sign goes. 6, 3, negative 9, negative 12, 24. We can perform one elementary row operation. Negative 3 times row 1 plus row 2 yields a new row 2. That does not change the first row. Negative 3 times 1 plus 3 is 0. Negative 3 times negative 3 is positive 9, plus negative 9 is 0. Negative 3 times negative 4 is positive 12, plus negative 12 is 0. Negative 3 times 6 is negative 18, plus 24 is positive 6. The last row represents the equation 0x plus 0y plus 0z equals 6. 0 equals 6. This is a contradiction. Whenever you get a row that's zeros except for the last entry and the last entry is non-zero, that represents a contradictory equation. The system is said to be inconsistent. This, by the way, is the symbol for a mathematical contradiction. It's two arrows colliding, two things that are not consistent with each other. The system is inconsistent. It has no solutions. The solution set is equal to the empty set. This symbol represents the empty set in mathematics, and only the empty set. The empty set is also denoted by braces that are empty. Suppose we start with this system. We'll write down the augmented array, 1, negative 2, 3, slash 9. 1, negative 1, 6, and then 15. 3, negative 7, 8, and then 26. If we take negative row 1 plus row 2 to yield a new row 2, we'll get a 0 under the first leading 1. We'll do negative 3 times row 1 plus row 3 yields a new row 3, giving us a 1 in the third row as well, under that first leading 1. The first row will stay unchanged. Negative 1 times 1 plus 1, negative 1 times this plus this, negative 1 times this plus this, negative 1 times this plus this, negative 3 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 times 9 is negative 27 plus 26 is negative 1. The next easy elementary row operation is to take the second row and add it to the third row. Row 2 plus row 3 yields a new row 3. That leaves the first two rows alone. Let's multiply the second row by 2 and add to the first row. Only the middle row stays unchanged. On the top row, we're taking 2 times the second row and adding it to the first row. That doesn't change this 1, but it does give us a 0 in this spot. 2 times 3 is 6, plus 3 is 9. 2 times 6 is 12, plus 9 is 21. Adding the second row to the third row gives us a 0 in this spot. We'll have 2, and then 5. We'll be in row-echelon form if we just multiply the last row through by 1/2. To obtain reduced row echelon form requires two more elementary row operations. The operations are -3 times row 3 plus row 2 yields a new row 2, and -9 times row 3 plus row 1 yields a new row 1. The third row stays as it is. We'll have 1, 0, 0, 0, 1, 0, 0, 0, 1 to the left of the vertical slash. We'll get zeros in these two positions by design. -3 times 5 halves is -15 halves, plus 12 halves is -3 halves. -9 times 5 halves is -45 halves, plus 42 halves gives you -3 halves. The solution set is the point -3 halves, -3 halves, 5 halves. I wanted to show you how to use your handheld calculator to do this. To enter the matrix, you press second matrix and then go to Edit. We, of course, are entering a 3x4 matrix. As you can see, I've entered most of the matrix here already. You can press second to quit to get out of that. To place the matrix in reduced row echelon form, you select second matrix math. Work up until you get to RREF and enter the matrix. It gives you the reduced row echelon form, but if you want it in fraction form, you have to press math and then frac. Next, we'll consider the overdetermined system given here. Putting this into an augmented array, 1, -1, 2, slash 4, 2, -1, 3, 10, 3, -3, 6, 10, 4, 2, 0, 7. We'll perform 3 elementary row operations to get zeros below this leading 1. So -2 times row 1 plus row 2 yields new row 2. -3 times row 1 plus row 2 yields row 3 yields a new row 3. And -4 times row 1 plus row 4 yields a new row 4. That leaves the first row untouched. -2 times this plus this. -2 times this plus this, -2 times this plus this, -2 times this plus this, -3 times this plus this, -3 times this plus this, -3 times this plus this, and -3 times this plus this. We can stop now. We can tell already that we have an inconsistent system. We have this equation 0 equals -2. That is a contradiction, and therefore it's inconsistent. The solution set is the empty set. I thought you should see how this works out on the calculator as well. I'm going to show you first that I've entered the matrix as a 4x4 array, and then you get second quit to get out of that. Second matrix, we're going to do the math again. Scroll up from the bottom, it's quickest, to get to RREF. Enter that. And then second matrix, I press 1 to enter the matrix. Hit enter. And notice that the last row is 0, 0, 0, 1. Suppose we have x minus 2y plus z equals 1, and 5x plus 2y equals 3. This system is underdetermined. We either have no solutions or infinitely many. Let's write the augmented array. We need to take negative 5 times row 1 and add to row 2 to yield a new row 2. It leaves the first row alone and gives us a 0 in this spot. Negative 5 times this plus this. Negative 5 times this plus this is 12. We'll have a negative 5 and then negative 2. To place this in reduced row echelon form, we still have to multiply through by 1/12 on the second row and then get a 0 above the leading one. So 1/12 row 2 yields a new row 2. We'll have negative 5/12 and negative 2/12 filling out the row. Then we need to take negative 2 times row 2 plus row 1, yielding a new row 1. That'll give us a 0 above the leading one in the second row. Positive 2. So positive 2 times 5 halves is going to be negative. Positive 2 times negative 5 halves is negative 5, plus 1 is negative 4. Positive 2 times 2/12, which is 1/6, negative 1/6, will be negative 1/3, plus 1 is 2/3. What is the solution to the system? There will be infinitely many solutions. As you can see, x and y will be determined by the variable z. If the second equation represents y minus 5 halves z equals negative 1/6, if we set z equal to t, and if the first equation represents x minus 4z equals 2/3, we can immediately write down the solution set. X is going to be 2/3 plus 4t. Y is going to be negative 1/6 plus 5 halves t, and of course z is t. T ranges throughout the entire set of real numbers. This will be the solution set, all points on that parametric line. Hopefully you didn't learn anything really new today. Going to row echelon form and back substituting gives you a method called Gaussian Elimination. Going all the way to reduced row echelon form gives you Gauss-Jordan elimination. Which is nice because if you go all the way down to Gauss-Jordan reduced row echelon form, you can usually just read the solution right off of the augmented matrix. Next time, we'll get a little more into matrix algebra.